showed you for the Kagame case. So the Kagame case, you remember there were kind of very extended features in momentum space. What we get here are features which are quite concentrated in momentum space at the locations of antiferromagnetic Bragg peaks. So you have to imagine that we have sort of dispersive spin waves coming up as a function of energy, and then we're chopping at some particular energy transfer, and then we get these kinds of features. My intensity scale is actually somewhat saturated, so this looks like just totally filled in. There are also some resolution effects that would give rise to that, but basically you have pretty sharp locations in momentum space where I can scatter neutrons inelastically. So that's in the ordered antiferromagnetic state. Now I'm going to heat up the system into the... Yes?
Why did you put the title Frustrated Paramagnet?
Oh yeah, sorry.
In the entity.
You're right, yeah. So that title belongs to the next picture.
Okay.
So this is not... That's a very good... this is not... This is the happy antiferromagnet, which has its sharp features in momentum space. But now I'm going to heat up into the frustrated paramagnet. So then the feature goes like that. So everything broadens out tremendously. This is at 205 Kelvin and in this paramagnetic insulating state. And you might ask, well, is that something specifically at this energy transfer? And the answer is no. This is actually across the whole bandwidth of excitations. Here I'm showing you the plot of energy momentum dependence of intensity with spin wave excitations at low temperatures. When I go into the paramagnetic insulating state, all of this collapses, and I have a very broad smudge, if you will, of magnetic scattering in this paramagnetic state. Now, in some ways you could say, well, this is not so surprising. You've gone into a paramagnetic state and you've lost the correlations. But I think what is special in this system is that the transition is so abrupt on the other side of this antiferromagnetic to paramagnetic transition, sort of just infinitesimally above, then all of the vestiges of the ordered antiferromagnetic state actually vanish, and things are really broad in momentum space. Now the underlying reason for that is that it is a first order phase transition, and it is a structural transition that really alters the exchange constants quite substantially. But now I want to understand, why is it that transition actually had...
How big are the displacements of this structural transition?
Those are probably 0.05 angstrom or something. It's pretty substantial.
0.05 angstrom.
Yeah. So it really is, you might call it an orbital occupational ordering transition, where the orbital degeneracy is lifted in going from...
In the low temperature phase.
Low temperature state, yeah. But the interesting feature that I now want to point out is that this paramagnetic state, I think that it is a strongly frustrated configuration, and this is where it comes from. So consider the honeycomb lattice. This Vito3 structure consists of pocket honeycomb lattices stacked on top of each other. And so it's good for us to look at the honeycomb lattice and think about the magnetism of the honeycomb lattice. And here I have shown on this lattice two exchange constants. So it could either be the near neighbor exchange constant here, which goes along the edges, or the next near neighbor exchange constant J2, which comes across like that, and there are several copies of that. So J1 is associated with this edge here. J2 is all of these weaker bonds. There can be actually competing interactions, and that can give rise to very interesting physics on the honeycomb lattice. So if I go to the case where J2 dominates, so if this one is a dominant interaction, then I end up with this kind of what?
You mean J1?
J1. J1. No. Yeah. Sorry. You're right. J1. Okay. Sorry about that. It's J1 dominant. J1 dominant. So then this becomes very small, and now you see that I am simply getting a nail antiferromagnet on the bipartite honeycomb lattice. So I have up spin here and then 3 down spins surrounding it. So that's a perfectly reasonable non-frustrated magnetic condition. On the other hand, if I go to very large J2, then it's this next neighbor interaction which should be satisfied. And so I see now this one. So if I take this spin here, it's anti-parallel to all of its neighbors linked by J2. On the other hand, the near-neighbor interaction is alternately, we have the correlations which are ferromagnetic and antiferromagnetic. So this one satisfies J2 but not J1. And then in between, in this range here, and actually this comes from a paper whose reference is down here. It's not the city Albuquerque, but someone called Albuquerque, PFP 2011, has written a nice paper on this. And in this range for the ratio of J2 to J1, there's either some form of a honeycomb singlet state, a valence bond crystal type state, or actually I think that's what he's talking about, mostly the valence bond crystal state that might be forming in this range of parameters. And then you could ask, where does V2O3 lie? And this is where the DFT work of Valenti and company, which is validated, I would argue, by the low temperature agreement between the measurements and the calculation, they actually place this ratio right here and quite close to that state. And so our claim is that because of the particular ratio of J2 to J1 for V2O3, that we actually end up with a paramagnetic state which is strongly frustrated, and actually the momentum dependence that we see experimentally is quite similar to what you would obtain in this kind of valence bond crystal state. So the answer to the question that I started with, which was why is this mod type transition exposed for V2O3? Our tentative suggestion is that it is actually exposed in a sense. The following argument, that if it had not been for the frustration associated with this honeycomb lattice, that then probably all of this would be engulfed by a Slater insulating state, and we would never see this phase boundary exposed. But because of suppressing, if you will, through frustration, that transition into the Néel ordered state, then we actually expose this mod transition.
Sorry?
Yes?
So how important is the out-of-plane couplings, right? Because in 2 dimensions, this fluctuation and so on, that can be really true. But I mean, there's always a 3D element to it. And so this can destroy this frustration quite a bit, right? So is there any estimate about these couplings?
Yeah, actually we have values for all of those couplings from calculations, but not from experiments. I mean, from experiments we just have the dynamic correlation function.
How does it influence the frustrated region?
So this is work in progress, not yet published, but various attempts have been made to calculate the spin correlations with the given LDA calculated exchange constants, and they do indicate a very deeply suppressed Néel temperature for that particular combination of exchange constants.
And this is like that order of
Yeah. Okay, so then I should just say that this is where the kind of the bridge to tomorrow, where we're going to talk about strongly correlated metallic systems. I don't think I'm going to say much more about this compound, but it is a beautiful compound because when you transition from the paramagnetic insulator to the paramagnetic metal, you actually have the development of a modulation that one can associate with the appearance of a Fermi surface. So the Umklapp 2KF process now shows up in the scattering data, and as you cool the system down to lower temperatures, then these features actually become sharper, and eventually you get a spin density wave state forming here. So in V2O3 you really have all of a lot of the interesting aspects of condensed matter physics hold, except perhaps for superconductivity. Okay, so then to summarize, I would say that we've seen various examples of using a technique that's developing quite rapidly at this point. And I talked quite a lot about the Herbert-Smithite spin system. I think it's a very important and interesting compound. I think the work illustrates some of the challenges experimentally in looking at resonating valence bonds in solids. It's really difficult, as far as I can see, to distinguish a dynamic configuration of singlets that is a truly resonating state of singlets from a static disordered configuration of singlets. That is something we don't really know how to do directly, and that means that disorder is always going to be there as a possible source of basically trapping the singlets due to such a disorder potential on the lattice. And experimentally, it's pretty difficult for us to separate those things apart. Okay, so I think that will be it. So thank you very much.
Just a few words. So first, sorry for the mistake that happened. Hope the lecturer and everyone is not so distracted too much. And secondly, it's due to that problem, we will have the afternoon's lecture and tomorrow's lecture in this classroom. We'll come back at 1 p.m.